Hello everybody. So, today's lecture is all about one thing and one thing only, and that is polynomial division, alright? So, in the spirit of that, I have a goal for today, and the goal is this. I want us to be able to consider minus 16 plus x to the fourth, all divided by x squared plus 4, and by the end of today's video, I would like us to be able to simplify this without factoring. Without factoring, alright? Because if we allow ourselves to factor, this isn't too hard of a simplification. Some of you can probably already see that the answer is x squared minus 4. But ideally, I would like to be able to simplify that using the techniques we talk about today. So with that in mind, let's go ahead and get right on into it. Okay, so to begin, I want to go ahead and go back and get a nice blast from the past, and I want to consider this problem. What is 1024 divided by 2? Now at this point, a lot of us can probably do that in our head real quick, and if others may take a couple seconds more, but at the end, we can all get there. Now, I'm going to say, we're working too fast. We got to slow things down for today's lecture. What do I mean by that? To solve this, we're going to go all the way back to the beginning and do some straight up long division. I just want to review, make sure we're all clear and we all remember how we do long division for today's lecture. So, how do we start this off? Can 2 go in the 1? No, we can't. Put a 0. Can 2 go in the 10? You can 5 times. 10, 0. You bring down the 2. You bring down the next value. Oh, and I guess I should emphasize that we have 10 minus 10, so that becomes 0. Then we bring down the 2. 2 can go into 2 one time. We get a 2. Again, we subtract. We have a 0. We bring down the 4. 2 can go into 4 2 times. We minus the 4. We get that 0. Alright, so hopefully this seems a bit familiar. It's jogging some memories how we do long division like this. Similarly, if and also definitely worth remembering is, let's change this problem up a tiny bit. Let's make this 1025. And let's do long division again. And I'll take this one a bit slower, just in case I went too fast on that first one. So again, to start off with long division, we write in our long division format. Okay, and we ask ourselves, how many times can 2 go into 1? It can't. How many times can 2 go into 10? 5. So we get, well, I guess you can just not write anything there instead. So you get 10, because 2 times 5 is 10. Then you subtract the 2 numbers. You get 0. You bring down the next number, so you get a 2. You repeat the process. That's how we get 1. 2 minus 0 again. Then we bring down the 5. Now 2 can't go into 5 wholly, but it can get pretty close by multiplying by 2 and getting 4. And when we do this subtraction, we're left with a 1. Now for those of you who don't remember, what does this mean for us, right? We have no other numbers to bring down, but we have a number left over. So this is what we call our remainder when we're doing long division. This is our remainder. And so that means our final answer takes the form of 512 plus 1/2, your remainder over the number you divided by. And that's how you handle that. So, just had to make sure we all reviewed that real quickly, because what we're going to be doing today, and all we're going to be doing today, is a bunch of long division. So we need to at least remember how the basic general process goes. Okay then, so before we actually get into talking about that, now we got to review some notation. Okay, so just to do some quick notation review, when we do a standard division problem, so something like f of x divided by d of x, let's say, and this will produce some result, something like q of x, and that may have a remainder, plus r of x over d of x. So this is the general way in which we can write a division algorithm, right? So we have 2 things being divided, it will produce a result with some possible remainder, alright? So just to review what all these terms mean, so we have an f of x, we have a d of x, we have a q of x, we have an r of x. All of these have meaning, alright? So f of x is what we call our dividend. D of x is what we call our divisor. Q of x is what we call our quotient. and then r of x is our remainder. So what are these exactly when you're solving a problem? Okay. So your dividend is usually, or it is, the thing you're dividing. What you are dividing. Your divisor is what you're dividing by. Your quotient is the result of the division. Good little smash there. And then your remainder is whatever's left over. Okay, and then a quick another terminology review is that if our remainder is 0, then we say the dividend and divisor divide evenly. But that's not that important. But so just to make sure we're familiar with these, because these words will be thrown about at certain points throughout the lecture, we have to understand that when I'm talking about dividend, I mean by the big thing I'm dividing by. When I'm talking about divisor, what I'm dividing with. When I'm talking about quotient, the result that was produced from the division. And when I'm talking about remainder, it's whatever is left over. Sometimes it's 0, sometimes it's not. So, just in case any of us have forgotten what these words were, and trust me, I had forgotten what some of these words were, here they are there. We're going to need to use them throughout today's lecture. So, if you haven't done so already, go ahead and pause and make sure you get this all copied down. Great, now let's finally get into polynomial division. Okay, so to start, when it comes to polynomial division, there are two big techniques. There is long division, and there's something known as synthetic division. Now, your textbook does cover synthetic division, and I'm sure some of you are probably familiar with it. However, I will not be covering it in today's lecture, and the reason being is I just really don't like synthetic division. In comparison to long division, which we're going to talk about next, it doesn't make sense. I don't understand why some of the procedures work. I haven't looked into it that much, but just from a face value, the process of synthetic division is weird, and even more of my gripe with it is that synthetic division can only be used in special circumstances. Only when you're encountering a certain type of division problem can you use the process of synthetic division. So, all this is basically summing up to, it is still a perfectly valid technique. If you know what synthetic division is, if you know how to properly use it, then go ahead and use it for this class. I won't stop you. For those of you who aren't familiar with synthetic division, don't even worry about it. We're going to learn a different technique, long division, which works 100% of the time and you never have to worry about. But I just yet again, I will not be covering synthetic division, but if you are familiar with it, or if you want to learn it, the textbook does talk about it. You can go look up and review more of it there. But with that out of the way, let's go ahead and get on into what we're going to talk about, which is long division. So long division of polynomials. And how we do this, the big secret behind this technique, and why I wanted to go back and review those long division numbers, is that pretty much the core of the process from long dividing numbers is going to carry over into the long division of polynomials. Core of the technique is exactly the same as when long dividing numbers. And so that's pretty nice, because what this means, and that the core of the process is the same, what that means for us is we don't have to bother learning a whole new technique. It's basically going to be taking this technique that we learned a long time ago and are familiar with, and just transitioning it to a new type of problem. So, that's pretty nice. Why don't we go ahead and jump straight to an example then? Okay, so to start things off, we're going to go ahead and consider the following example. 12 minus 6x squared plus x cubed plus 5x, all divided by x minus 4. And we want to long divide this. Okay? So, well, let's go ahead and write it into our long division form. That being x minus 4, then we have our division, 12 minus 6x squared plus x cubed plus 5x. Now, before we actually start the long division process, there's something I don't like about this. There's something I don't like about how this long division has currently been written. And it, to be more specific, something about the polynomials, or one polynomial in particular. So what is it that I don't like? Actually, take a moment, think about it, see if you can figure out what is it that I don't like about this in regards to one of the polynomials. Okay, so what I don't like is our dividend polynomial. And what I don't like about it is that, to me, it's not written the natural way I would write a polynomial. To me, the natural way, and the way all polynomials should be written, is in descending order of power. So that's not how this one is written. So a very important step, and actually a necessary step, something you must do if you are long dividing polynomials, is always make sure both the dividend and the divisor are written in their natural way of writing a polynomial, or in other words, always make sure the dividend and divisor are written in descending order of power. In other words, I would want to rewrite this as x cubed minus 6x squared plus 5x plus 12. Again, it may seem like a trivial step, but as we start the process of this long division, you'll see it's a necessary step, and it's something we actually have to do. So right there will be our first important note. As you can see, I'm kind of hopefully going to have a nice column off the side where we can keep important notes. And there's our first one, is always rewrite the polynomials. And it could be the divisor too. In this example, it was just the dividend, but maybe you have to reorder your divisor too sometimes. Always rewrite the polynomials in descending order, order of power. Okay, so with that out of the way, we can actually start our long division process now. So how are we going to start it off? How will we actually long divide these polynomials? Well, the key and the core of the process is going to lie with the highest degree power, or the variables with the largest powers in both the dividend and divisor. So for us, the divisor, the variable with the largest power is x, and for us in the dividend, the variable with the largest power is x cubed. So what are you going to do with these? Well, if we take a quick step back to our long division of numbers, and we consider 2 divided by 1025 again, right? How do we start things off? Well, I said, how many times can 2 be multiplied into 1? It can't. How many times can 2 be multiplied into 10? 5. And what that successfully let me do is that made me turn the 2 into a 10, and then I could subtract them away. So that's exactly what we're going to do in long division of polynomials. Like I said, the core of the process still carries over from the process from dividing numbers. So when it comes to dividing polynomials, the general idea of matching these values still remains the same. So I just want to match x with x cubed. That's all I want to do. I need to ask myself, what value can I multiply x by in order to make it an x cubed? So try to think about that for a second. Think in our heads. Yeah. And hopefully what we'll be able to come up with is that in order to match x with x cubed, I need to multiply by an x squared. Okay? So I will need to multiply by an x squared. So I want to match x with x cubed. So multiply by an x squared. Alright? That's how the process is generally going to go. You always want to be continually matching the highest degree, or the variable with the highest degree in your divisor, with the variable in the highest degree in the dividend. And there will be our second important note, is to start the long division match. We want to match them. Match the variable with the highest or largest degree or power in the divisor with the variable with the highest degree in the dividend. Or let me use the other wording, just with the largest power in the dividend. So, just to emphasize, highest degree and largest power are two different ways of saying the same thing, with the largest power in the dividend. Dividend. Ooh, I've already forgotten how to spell dividend. Just another D. Okay, and there you go. This important note right here, which is a very important note, we're going to triple star it, is how the whole process goes. It's just this constant process of matching variables with and making sure that they look exactly the same. So, to start this one off, I'm going to want to multiply x by x squared in order to match it with that x cubed, and that's exactly how we'll start this whole long division process. So in order to do that, I'm going to erase this quick note right here. So if you have this, don't have this written down, try to write off to the side somewhere just to understand what we're doing, but I'm going to need to erase it now. Okay then, so I want to multiply by an x squared. Now, what's going to be important to understand, and what we're going to need, it's going to actually be very helpful for us as we move through these problems, is after you understand you want to multiply an x squared, always try your best, and always just do this, is when you write the x squared, whatever you write, what you're going to multiply by up top, always match it with the corresponding variable that has the same power in your dividend. In other words, I wouldn't write the x squared right here, because that would be lining it up with the x cubed. And I wouldn't write the x squared over here because that'd be lining up with the 12. I'm going to write the x squared right here because that's where it's going to line up with the x squared in the dividend. So that's actually a pretty important note. So sadly, I'm going to have to erase one of our important notes. I'm going to erase the top one from our list right here. So you haven't already written the top important notes, go and pause the video and get that written down right now. Okay. Okay, yeah, so just to restate what I said again, line up what you multiply by with the similar term in the divisor, or the dividends, with the similar term in the dividend. In other words, I multiply an x squared, so I made sure to line it up with the x squared term in the dividend. Now then, we go ahead and let's do the multiplication now. Now, of course, I have to consider all of x squared minus 4, so I'm not just going to multiply, I have to consider all of x minus 4, my bad. So I'm not just going to multiply the x squared to the x, I'm going to multiply it to all of my divisor. So what I'm going to get is x cubed minus 4x squared. Now what's going to be very important is we're going to need to make sure to write parentheses around what the product of our multiplication, or the result of our multiplication. Always make sure to write those parentheses, because that's going to help us remember a very important idea, because again, going back to our division of numbers, what was the next thing we did? At this point we subtracted. We're going to do the same thing here. We were going to subtract, and why those why writing that parentheses is so important is because writing that parentheses is going to help us to remember that when we subtract, I need to distribute this negative to the minus 4x. It's a very, very common mistake when doing long division of polynomials to forget to distribute the negative over to this side over here, and it totally throws off your whole problem if you just make that one minor mistake. So this is a very important note. And it's actually going to go directly into the work and not even to our column, and that is always write the parentheses to help remember. Ooh, actually, you know what? Looking at my thinking ahead, I'm actually not going to be able to write that there. Silly, silly me. Okay, again, I'm going to have to erase this top important note. I want to make sure I leave this one. So go ahead and pause the video now and get that one written down if you don't already have it. Okay. So this note goes right here, and it's always write the parentheses to help remember to distribute the negative. Alright, we are subtracting, so we always need to remember to distribute that negative. Well then, from here, we just go ahead and do our subtraction. I'm going to have x cubed minus x cubed. That's going to give us a nice 0. Then I'm going to have, after I distribute that negative, I'm going to have a positive 4x there. So I'm going to have minus 6x squared plus 4x squared. It's going to give me a minus 2x squared. Beautiful. All right. And then just like with our numbers, what do we do in numbers? After we did our subtraction, we pull down the next number. All we want to do from here is pull down, actually, I don't like that crooked line. I'm going to go ahead and fix that up. We're going to get minus 2x squared. So, just like with the numbers, we want to pull down the next term. So I want to pull down that plus 5x. And there it is. There's one cycle from the long division process. And then from here, all it comes down to is just repeating this cycle. Here's the new polynomial. I now want to match x here with the minus 2x squared. So that means I need to multiply by a minus x, or minus 2x. Okay, so let me slow that back down and restate what just happened here. So I just completed one cycle of my long division process. Now all the process becomes is just constantly redoing that cycle. So what does that mean for us? Is that I want to match these terms. Just a quick note, I'm going to be erasing this because I need the room for the work. So if you're writing along with me, try not to write what I'm writing in the exact same spot. Write it off to the side somewhere. So again, I just want to repeat the process. Repeat the process. And match these terms. Right? So, and then why do I want to match these terms? Well, yet again, I want to take the variable with the largest power in my divisor, so x, and then technically this isn't the dividend anymore, but this is the new equation we're looking at, and I want to match with its highest, I want to match with the variable with the highest degree there, so that's the minus 2x squared, okay? So that tells me I need to multiply by a minus 2x, because if I want to make x and minus 2x squared, that's what I need to multiply by. So there you go. So with that understanding, I go ahead and multiply that value, and again I'm going to erase this quick note. So if you haven't copied it down off to the side somewhere, go ahead and do so now. Okay. Great. So then, I understand I need to multiply by minus 2x, so this is going to become minus 2x squared plus 8x. Okay, and again, I'm just going to do my subtraction. Like I said, we're just repeating the process at this point. So I'm going to do my subtraction. I'm going to remember to write these parentheses to help me to understand I need to be distributing this negative sign. So I'm going to get a 0 because minus 2x minus 2x is 0. Then I'm going to distribute that negative here. So I'm going to have 5x minus 8x. So I'm going to get a minus 3x. Great. Then I want to bring down my next term. So a plus 12. And then I repeat the process again. Here's the largest, again, the largest term in the divisor is x. Here the variable with the largest degree in this new equation is minus 3x. I want to match these. So how do I make x into minus 3x? I multiply by a minus 3. And again, I want to make sure I line up this minus 3 with the similar term in my dividend. Minus 3 is a constant, 12 is a constant, so I want to write it right there. There we go, and then we just do our multiplication. So I have minus 3x plus 12. Remember to write that parentheses. Then I go ahead and do my subtraction, and I'm going to get an end result of 0. And of course, from here, we end our long division process. Why do we do that? Because I no longer have any terms to bring down, so there's nothing left to do. It's over. And there it is. So that means, well, yeah, we'll get to that in a sec, how to write the final answer. Just for now, let's go ahead and absorb all this. Here we have just gone through a whole entire process of long dividing two polynomial functions, keeping note of some of the important notes along the way. So just to reiterate what happened here, okay, we started off by writing in our long division form. Then after we wrote in our long division form, we reordered the polynomials into their proper or natural order of descending powers. That was our second thing we did. What did we do in our third step? Well, we actually started the long division process. And to start the long division process, we take the variable with the largest power in the divisor, we take the variable with the largest power in the dividend, and I ask myself, what do I need to multiply in order to make these match? So for us, that meant taking x, multiplying x by an x squared, and doing that gave me the x cubed. And then I remembered that when I'm multiplying, I need to multiply to all of the divisors, so I get x cubed minus 4x squared. Beautiful. And then from there, it's just like when you divide with numbers, you subtract, but unlike when we divide with numbers, we make sure we write these parentheses. Why do we do that? Because that helps us to remember we need to distribute our negative, and then we go through our process of subtraction, we get whatever result is left over, and then we make sure to pull down the next term, just like we do with numbers. And after I pull down the next term, I repeat the process. Just a repetition of everything I just said. Again, I ask myself, how do I match x with the largest term here, which is minus 2x squared? Let's actually underline that blue. After I match them, which for us meant multiplying by a minus 2x, again I repeat the process, do my multiplication, put my parentheses, subtract the values. When I'm subtracting, I wrote those parentheses to help me remember I need to distribute that negative, repeat the process, get down to here, do it all over again one more time, and at the very end, we get that remainder of 0. We have no other terms to pull down. We are done. Okay, so now let's talk about how do we write the final answer, all right? So how do we write the final answer? And I guess I will go ahead and just erase this work right here. So if you haven't already done so, go and pause the video to make sure you get all this work written down. Okay. So this one, sadly, won't be able to illustrate what I want to talk about when it comes to writing final answers too well, because it doesn't have a remainder, but we can still talk about it. So let's go and recall real briefly that for the generic notation of this whole division process, we had f of x divided by q of x, oh no, my bad, divided by d of x equals q of x plus r of x divided by d of x, okay? And this general form is the way we write our final answers for these problems. Another way we can write the final answer, there's two acceptable ways. Here's the first one. And the second way we can write our final answer is like this. F of x equals q of x times d of x plus r of x. Okay, and actually let's not call this recall, let's call this ways to write final answer. So there's two ways we can write our final answer when it comes to long division, at least formally. There's the one way in which we have whatever problem we started with, so this, and this would equal our quotients plus whatever remainder term. And then the second way is to take the dividend and say this equals your divisor times your quotient plus a remainder. So just to give it a bit more of a concrete meaning, for this problem, how we would write our final answer is one of two ways, and they would look like this. So if you haven't paused the video to copy this down. Okay, so what I'm trying to get at is, at least for this problem, the ways in which we would write our final answer are 12 minus 6 squared plus 5x equals squared minus 2x. So we'd write the final answer like this. We have our dividend divided by the divisor equals our quotient, and we have no remainder for this problem, so there's nothing to add on. Or the second way we can write it is 12 minus 6x squared plus x cubed plus 5x equals x squared minus 2x minus 3 times x minus 4. And this is the second way in which we could formally write our final answer, is that our dividend equals the product of the quotient times the divisor. And of course, again, we add nothing because we have no remainder for this problem. So there you go. Just a quick understanding. If we're writing final answers, like on an exam or something, these are the two ways in which we present our final answer. And there you go. There's our first example of long division of polynomials. And let's just go ahead and get straight into another one. Okay, so I lied briefly. Actually, before we get into another example, we need to mention these two theorems because they'll be helpful moving forward. And the two theorems are this. The first one is known as the Remainder Theorem. And it's actually a pretty nifty theorem, and it says the following. If a polynomial is divided by x minus k, then the remainder is r equals f of k. So this is a pretty neat theorem in that it tells us if I ever divide any polynomial by a linear polynomial, so what's the key feature about that is that it's linear. So if I ever divide any polynomial by a linear polynomial, then I can guaranteed understand that the remainder of that division must be f eval, or the function. So I guess I should say that this f of x is, or this function f is coming from the polynomial. So the remainder of your division must be the constant term from your linear equation plugged into the polynomial you're dividing by. So that's a pretty nifty theorem, and we'll actually use it in our next example. We'll see how that works. And then the second theorem, the factor theorem, says, so this is actually this is a theorem you don't use explicitly, but the understanding of it is a very helpful tool. So the factor theorem says that a polynomial f of x has a factor x minus k if and only if f of k equals 0. So the factor theorem says a polynomial f of x has a factor if and only, or has a factor x minus k if and only if f of k equals 0. So this is actually a direct result of the remainder theorem, because remember, the only time in which we can say we divide evenly is when you have a remainder of 0. So basically that's what this is saying, right? If I'm dividing by some linear term, then remainder theorem tells me that you plug it into your function, and whatever that outputs is your remainder. So if I plug it into my function and I output 0, that means I have a remainder 0. That means I'm dividing evenly. And something we haven't discussed, but is true, is that if you divide a polynomial by a linear term and you divide evenly, then that must be a factor of your polynomial. So that's exactly what this factor theorem is saying, is that if you ever divide, and if you ever are able to evenly divide by a linear term when using a polynomial function, then that linear term must be a factor of your polynomial function. Like I said, that's something you use, like, it's not like you ever say, haha, I'm using factor theorem here, but it's something that we kind of just do unconsciously when we're solving math equations all the time. So very two useful theorems, and we'll actually see them in the next example. So let's go ahead and get into it. Okay, so for our next example, let's consider the following division. 3x cubed minus 6x squared plus 7x minus 2, all divided by x minus 1. And to just go ahead and spoil the problem real quick, this will be one with a remainder. Alright, so let's go ahead and just walk through our division again. So we'll start by writing in our long division form. And I'm going to actually, let's write this up. More room. We're going to have 3x cubed, 3x cubed minus 7x minus 2. Great. So then, let's go ahead and start our division. Again, just like before, I want to match x and 3x cubed, so I need to multiply by a 3x squared. Again, we'll remember to write those parentheses to help me understand I need to distribute that subtraction, and the result I'm going to get is a 0 and a minus 3x squared. Okay, so just to run through it one more time because we're still trying to get used to this. How did I start this process? I wanted to match x and 3x cubed. That means I need to multiply by a 3x squared. So I multiply my divisor by 3x squared, and then I want to subtract. So because I'm subtracting, I remember to write my parentheses to help me recall I'm going to need to distribute that negative over here. Then I run through my subtraction. 3x cubed minus 3x cubed is 0. Minus 6x squared. And since I distributed the negative, it's going to be minus 6x squared plus 3x squared, giving me minus 3x squared. And then I want to bring down the next term, so I'm going to plus 7x, and I'm just going to repeat the process again. So I want to match minus 3x squared and x, so I need to multiply by a minus 3x. I do my multiplication. I'm going to get a minus 3x squared plus 3x. Write my parentheses, subtract. I'm going to get a 0, and then I'm going to get a 4x. Okay, beautiful. Bring down the next term. Minus 2. I want to match 4x and x. I need to multiply by a 4 plus 4. So then I have 4x minus 4. I subtract again, writing my parentheses, and so I get a remainder of 2. Alright, how do I know I have a remainder of 2? Why do I stop here and say this is my remainder? Right? Why do I stop here and know that's my remainder? Because I have no other terms to bring down. Okay, and there you go. So now we have to write our final answer. And of course, remember, there are 2 ways in which we can express our final answer. So just so I don't have to erase anything, I will go ahead and write the final answer this way. So this problem will equal 3x squared minus 3x plus 4 plus, and since I have a remainder, I do need to be adding something on this time. It's going to be plus my remainder divided by the divisor. So plus 2 divided by x minus 1. And there you go. That's how you would write one formal way of writing the final answer. Of course, there is the other way. There is another way in which we can write this final answer. I actually encourage you to try writing it that way on your own as well. But there you go. So there's this problem, and here's an example of what happens when we log divide with polynomials with a remainder. Just like with numbers, it's not scary. All it basically means is at the end, we do the same exact process, nothing changes, and at the end, there's just a leftover term. We have to make sure we understand how to properly write when we express our final answer. That's all remainders are. Nothing to be scared about. So, there we go. Oh, one quick note I guess I should mention is that in this example, the remainder was a single number. It was 2. But what we'll see in future examples, and probably on your homework, is that the remainder doesn't necessarily have to be a single number. Since we are dividing polynomials, the remainder could have been like something like x minus 1. But that's for later in this lecture. Just thought I'd mention it now. But there we go. So there's this example. Go ahead and pause the video now to get all this work written down, and we'll move on to the next one. Okay, so for our next example, it's your guys' turn. So I want you all to consider the following division. 2x squared plus x minus 11, all divided by x plus 5. So at this point, I would like you all to go and pause the video, try working through this problem on your own, and we'll go ahead and compare. After you unpause, we're going to just compare answers. I'm not going to show any of my work, we're just going to compare, and hopefully we get the same thing. So at this point, go and pause the video now. Alright, so the answer that I got, I got 2x squared plus x minus 11 equals 2x minus 9 times x plus 5 plus 34. So this is that second way of formally writing our final answer. If you wrote it the other way, that's totally fine. Just make sure that the proper terms match. So what I mean is that 2x squared plus x minus 11 is my dividend. 2x minus 9 is my quotient. So in other words, 2x minus 9 was the value was the equation I produced from my division, was 2x minus 9. X plus 5 is my divisor. And I had a remainder of 34 at the end. So you didn't need to write it this way. Remember, there is the second way of writing our final answer formally. But just make sure that these were the same terms that you got. So beautiful. Like always, if you did not get the same answer as me, don't automatically assume you're right. Or don't automatically assume that I'm right and you're wrong. Double check your work. I could have made a mistake. And if you think so, go ahead and email me. And we'll go and discuss. And I have just realized that in the previous example, we never used the remainder theorem like I said we would. So let's actually go ahead and use the remainder theorem here. So what does the remainder theorem say? Well, since I'm dividing by a linear term, x plus 5, the remainder theorem says that if I take my k from here, and k will be minus 5, and I plug that into my function, f of x, and f of x will be the dividend, so 2x squared plus x minus 11. So in other words, if I take minus 5 and I plug it into that function, whatever that outputs, that is guaranteed to be the remainder of our division. So let's actually check. Let's plug negative 5 in and let's see if we output 34. Because if we do, then that's a pretty good indication that my answer is correct. So let's go ahead and check it out. F of minus 5 equals 2 times minus 5 squared plus minus 5 minus 11. So we're going to have minus 5 squared is 25. 25 times 2 is 50. So I have 50 minus 5 minus 11. 50 minus 5 is 45. And then 45 minus 11 is indeed positive 34. So there you go. It checks out. The remainder I got from my division is the same remainder that the remainder theorem tells me I should have. So that's a pretty good indication that actually my final answer is correct. So there's the point I was trying to get out with this remainder theorem is that if you go through a division, if you go through any division, no matter if you get zero remainder or any remainder, always take the time to try plugging in, I guess I should say, if you are doing a division where the remainder theorem is applicable, in other words, if you're doing a division with a linear term, then it's actually worth at the very end to quickly use the remainder theorem to see if the remainders you got from your division and what the theorem tells you match up. Again, I want to emphasize that the remainder theorem is only applicable, you could only use it if you're dividing by a linear term. We're actually going to do a couple examples towards the end where we don't divide by a linear term. So in those examples, the remainder theorem would not be applicable. But that's for later. For now, let's go ahead and move on to our next example. Okay, so for our next example, let's go ahead and consider the following division. X cubed plus 8 divided by x plus 2. Alright, so let's go ahead and start it off by writing in our long division form. Great. As always, I want to match the two terms, x and x cubed. So I'm going to need to multiply by an x squared. No problem. Now, as always, we're going to go ahead and line up our x squared that we're multiplying by with the x squared and the dividend. That's weird. I don't have an x squared to line up with. Oh well, probably not that important. Just go ahead and write the x squared right there. Okay, so then we do our multiplication, and we get x cubed plus 2x squared. Great. Got to remember to write those parentheses in order to help me remember I need to distribute that negative, and then I'll go and do my subtraction. X cubed minus x cubed, 0. Easy peasy. Then we have 8 minus 2x squared. Huh. That's weird. It wants me to do 8 minus 2x squared. But those can't, well, that expression can't be simplified. So what the heck do I do with that? Okay, so what I'm trying to get at here is that if you ever find yourself in a long division problem, and as you're working through it, you have those two situations where it kind of just makes you go, huh? The first one being, we didn't have an x squared to line up with. In the dividend. Right, so that first kind of huh moment was, I went to try to line up my x squared I multiplied by with the x squared in the dividend, but there wasn't one. And then the next kind of huh moment was, I needed to subtract, or I have an expression that can't be simplified. That was the next kind of a what moment? So if you ever encounter either of these as you're working through a long division problem, what this means and what the title of this example alludes to is that you're missing terms in your long division. So the prominent one for what we've worked through so far is that we're missing an x squared term. Okay? And what this means and what is true for all long division problems is the following important notes. So whenever you're doing a long division of polynomials, you always need to have terms for every power smaller than the largest power in the dividend and divisor respectively. Whatever. So the important note is that if you're ever doing long division of polynomials, you always have to make sure that you have terms for every power smaller than whatever your highest power is. So for example, in this dividend expression, the highest power is x cubed. So that means I need to make sure I have an x squared, I have an x, and I have a constant. So I have my constant, good, but I'm missing an x squared and an x term. So I need to figure out ways in order to bring those terms in. You also need to double check for your divisor. But the divisor, we're all good because the highest power is 1, so I just need an x and some constant term. That's no problem. Okay? So, the question then becomes, well, I'm missing an x squared term and I'm missing an x term, so how can I sneak those values into this equation? How can I do that? And I don't know who came up with this, but whoever did, it's kind of this, wow, that makes so much sense thing. But I'm sure it was a really big thing to whoever came up with it first. And whoever did come up with it first, excuse my language, they are real badass in math, because this is such a really simple but such an effective little trick that we're about to do, and it's used so often. And yeah, well, it's just one of those things you just got to appreciate, whoever came up with this. Okay, so what the trick is this. And I guess I'm going to go ahead and erase this important note right here. So this is a very important note. If you don't, go ahead and make sure you definitely pause the video right now to get this copied down. Okay, so here's the trick. So, for whatever terms you are missing. So for us, it's an x squared and an x. So for whatever terms you are missing, what you do is you add in the missing term with a 0 coefficient. Add in the missing terms with the 0 coefficient, or coefficients. Alright, so add in with 0 coefficients. What exactly do I mean by that? So, well, let's go ahead and just start our work from scratch. And what I encourage you, if you haven't done so already, what I encourage you is don't erase your work. Just put a giant X through it. Because it's worth remembering, it's worth having this scratch work there to understand that we tried working through it this way. We understood that there was an error here, so we're just going to cross it out and we're going to start over again. Now, I don't have the board space, so I have to erase. But I encourage you not to erase and to leave this here to just remind yourself that if you see something like this, that means it's a no-go. Alright then, so what do I mean, what exactly do I mean with this little trick right here? I mean this. So when I start my long division, alright, so I start with my x cubed. Now I want my x squared term to show up next, because remember we want to keep this in descending order. So I want to add it in, and I want to add it in with a 0 coefficient. Well, remember, when we say the word coefficient, that's the multiple, that's the constant being multiplied to a variable. That's what coefficient is to us. So I just want that coefficient to be 0. So I add in a plus 0x squared. Great. And then I have to move on to my next term. Now in descending order, that means my next term is x. Again, I'm missing an x, so I also want to be adding in a 0x. And then I tack on that constant at the very end, plus 8. And so this is what it means to add in those missing terms with 0 coefficient. And why are we allowed to do this? Well, remember, what does it mean to multiply anything by 0? What happens? It just becomes 0. So 0x squared is 0. 0x is 0. What does it mean to add 0 to a number? It means nothing. You do nothing. You change nothing. So we are successfully, with this trick, we are successfully introducing an x squared term and introducing an x term without changing our equation at all. I don't know about you guys, but that's just like, wow, that's mind-blowing. That's so cool. You are making this thing look so different than what it actually is, but you're changing nothing about it. And you're getting to use these terms that we're missing without affecting the problem as a whole. That's just such a really cool and powerful trick, and it's used quite often throughout math. But regardless, this is how we're going to use it here. And now we can go ahead and just run through our division. Once we introduce these 0 terms, it just becomes just another standard division problem, and you just walk through with your normal process. So for us, again, so unlike before, we now have a place to match up our x squared term. So we get x cubed plus 2x squared. Beautiful. And then we want to subtract. And now, unlike before, right, we're going to have the 0, and unlike before, we have an x squared and an x squared we're subtracting. They're common terms. We can actually simplify that expression down. We get minus 2x squared. I bring down my next term, and my next term is the 0x. All right? So we're not going to bring down the 8. We're going to bring down, we're going to bring down the 0x. And then I just continue with my normal process. I want to match minus 2x squared and x, so I need to multiply by a minus 2x. So I get minus 2x squared minus 4x. Remembering to put my parentheses to help me understand I need to distribute. So I'm going to get a positive 4x. I bring down the next term, plus 8. And then I'm going to multiply by, I want to match 4x and x, so I'm going to multiply by 4, so I have plus 4 up there, and I get 4x plus 8. Subtract these, and I get 0. Wonderful. So, my final answer is that x cubed plus 8 divided by x plus 2 equals x squared minus 2x plus 4. There we are. Okay, so again, this is probably the most important example from today because it just illustrates a very helpful technique and a very common situation to encounter when long dividing polynomials. And people often forget that an easy fix to this problem, because without this zero trick, the problem becomes quite weird and quite difficult if we don't understand this zero trick. But with this zero coefficient trick, we understand how to use it. We just simply plug those missing terms into our polynomials and the problem becomes just like any other long division problem. And we just walk through it, simple as that. So there it is. Go ahead and pause the video now to copy this work down, and then we'll go ahead and move on to our next example. Okay, so again, it's your guys' turn, and I want you guys to consider this following division. X to the fourth plus 3x squared plus 1 divided by x minus 1. So again, I would like you guys to go ahead and try working through this problem on your own and come up with the results. Alright, so I'm going to give you a quick hint just to help you guys along. The hint is this. For this division, there are two missing terms. So you're going to need to use this zero coefficient trick we just talked about in order to introduce these missing terms. But with that said, go ahead and pause the video now, try working through the problem on your own, and after you unpause, I'm simply going to write my answer and we're going to compare our results. So go ahead and pause now. Okay, so hopefully you worked through the problem, and let's go ahead and compare our results. So the answer I got for this problem was x cubed plus x squared plus 4x plus 4, and I had a remainder of 5. So this is the formal way I'm going to write my answer. But just to say, the quotient, or the result I produced for my division was x cubed plus x squared plus 4x plus 4, and I had a remainder of 5 after I'd worked through all my division. So again, hopefully we got the same answer. If we didn't, don't automatically assume you're wrong and I'm right. Double check your work, and if you feel confident in your answer, email me and we can go and talk about it there. With that said though, let's go ahead and move on to our next example. Okay, so let's do our next example now. And our next example, as the name implies, what's going to be special about this one is that it has a non-linear divisor. Right there, the divisor is 2x squared plus 1. That is, of course, non-linear. We actually know what that is. That's quadratic. And let's go ahead and see how this changes the problem, right? It doesn't change it too much, just a couple more things we have to keep track of is all. Oh, and also, quick side note is how I mentioned before with that remainder theorem. So this right here is an example of a problem in which you cannot use the remainder theorem because our divisor is non-linear. Just a quick side note. So let's go ahead and jump right into the problem. Divided by 6x cubed plus squared plus x plus 8. Okay, and so before we even start, here's our problem written in long division form. Before we even start, we're going to take note of something. And what we're going to take note of is exactly what we talked about in the previous two examples, in that there is a missing term for this problem. So what I encourage you now is go and pause the video and try to figure out where the missing term is, and then we'll talk about it after you unpause. So go ahead and pause now. Okay, so the missing term, if you're able to see it, isn't in the dividend this time, but we actually have a missing term in our divisor, right? Because the highest power in our divisor is x squared, so that means we need an x squared term, we need an x term, and we need a constant. But we don't have an x term. We're missing that x term. So, missing x term in divisor. Alright. What does that mean we need to do? Well, all it means is we just need to apply that zero coefficient trick here, right? So like I mentioned in that note at the very start, when we first introduced the zero coefficient trick, is that you may need to do it for both the dividend and the divisor, alright? It's not, it may not ever be that it's only the dividend that needs to introduce zero terms. the divisor, sometimes you need to add those terms in as well. So we'll go ahead and do that now. So I guess it'll no longer be important. But so then by introducing that 0 term, we're then going to have 2x squared plus 0x and then plus 1. There it is. Alright, so now we can go ahead and just run through our division. So, how did I say, what was, when we first talked about division of polynomials, what was our first step we said? We said take the largest power in your dividend, take the largest power in your divisor, make them match. I have a 6x cubed in my dividend, that's the largest power. I have a 2x squared in my divisor, that's the largest power. I want to make them match. In other words, what do I need to multiply a 2x squared by to make it match with 6x cubed? So think about that for a second. Alright, so the answer is 3x. So, I go match the 3x with the x term in my dividend, and I simply do my multiplication. So I multiply 3x to all of my divisor, and so I get 6x cubed plus 0x plus 3x. So hopefully at this point, what you can start gathering is that when you have nonlinear divisors, the process doesn't change at all. The only real thing that changes is in your subtraction step, you're just going to be subtracting more terms is all. That's the only big difference. So then, we go ahead and do our subtraction. 6x cubed minus 6x cubed is 0. I'm going to have a 10x squared. And then I distribute that negative, so I have x minus 3x. So I have minus 2x. Okay? And now, what's important to realize is you always want to have enough terms match when you start your division process. You always want to have enough terms to be matching with the divisor. So here I only have 2 terms, but my divisor has 3 terms. So I need to be bringing down another term. So I'm going to bring down that plus 8. Because that's going to guarantee me the 3 terms I need to match with the 3 terms in my divisor. Okay? So that's a note worth. So for nonlinear divisors, always make sure to have enough terms matching. Alright, so what am I trying to get at? We have 3 terms here, so we need to make sure we have 3 terms there. Alright, so then we just repeat the process. I have a 2x squared. I want to match it with a 10x squared. What do I need to multiply by? 5. So I'm going to add 5. Then I'm going to get 10x squared plus 0x plus 5. Write my parentheses to help me remember I need to subtract. We do our subtraction. And then what we're going to get is 0 minus 2x, and we distribute the negative, so we have plus 3. And there you go. Right? So we have to ask ourselves, well, I still have a variable there, so do I stop my division? Well, when do you know to stop your division? You know when you have no other terms to pull down. So, do I have another term to pull down? Nope. That means I do actually need to stop my division. And as I briefly mentioned before, this is just because we have a variable left isn't a big deal. All that means is our remainder has a variable. Not that big of a deal to worry about. Just make sure you properly express that in your final answer. Let's go ahead and do that now. So I'm going to go ahead and erase this little blue note because it just might get in the way. So that means our final answer is that this division equals 3x plus 5 plus minus 2x plus 3 all divided by 2x squared plus 1. So my quotient is 3x plus 5 and my remainder is minus 2x plus 3. Again, not that big of a deal to have a variable in our remainder. We are dividing polynomials. These polynomials do have variables, so we shouldn't be too freaked out that a variable showed up in our remainder. And there you go. There's a quick example of a nonlinear divisor. The important point about this example is that we had to introduce a zero term in our divisor, which sometimes we have to do. Again, nothing to freak out about. Just have to remember to make sure we do that. Okay, so with that out of the way, go ahead and take a moment to pause the video and get this all copied down, and we'll go ahead and do our next example. Okay, so I'm going to go ahead and erase all this. So let's go ahead and do another nonlinear example. We'll do 5x to the 4th plus 10x cubed minus x squared plus 28x minus 39. This is a long one. We'll divide this by x squared plus 2x minus 4. Okay, so here's our next example. 5x to the 4th plus 10x cubed minus 7x squared plus 28x minus 39, all divided by x squared plus 2x minus 4. Now that's really long, and I'm tired, so it's your guys' turn. Go ahead and work through this example and see what you get, and then, I'm starting to get tired. So go ahead and pause the video now, work through this example, see what you get, and after you unpause, we'll go ahead and compare our answers. So go ahead and pause the video now. Okay, so let's go ahead and compare our answers. And the answer that I got for this problem was 5x squared plus 13 plus 2x plus 13 divided by x squared plus 2x minus 4. So let's go ahead and compare. Hopefully we got the same thing. If we didn't, don't be confident that you're wrong, or don't be sure that you're wrong and I'm right. Double check your work. It could be the other way around. And if you feel so, make sure you email me. But just to iterate again, I got a quotient of 5x squared plus 13, and I have a remainder of 2x plus 13. So there it is. There's that example. Let's go ahead and move on to the next. Now, for our next example, as a reward for all of you who made it to the end of the video, I have this little special treat. Remember that goal problem at the very beginning? Our goal problem was minus 16 plus x to the 4th divided by x squared plus 4. Here's my special treat for you for having sat through this video and made it to the end. Go ahead and do this problem. We already know what the answer is. The answer is x squared minus 4. Go ahead and do the long division. The long division, show me your work, write all the work down, email that work to me, and I'll give you 5 points extra credit towards your lowest homework assignments. So, just thought I'd give you guys that nice little treat if you manage to make it to the end of the video. Again, write up the work for the long division, email that to me, and you'll get 5 points extra credit towards your lowest homework assignments. Besides that, that's it for today's lectures, guys. I hope everyone's still having a good time out there, locked up, doing that self-quarantine. Make sure you stay safe, make sure you stay healthy, and I'll catch you guys in the next video. See you later.